All right, so welcome back. This is Steve Scully. I'm reading again through the instruction manual as it is written in the Cosmos and picking up where we left off. We're in Chapter 2, Section B, the Big Bang's Big Assumption. The Big Bang model says that all distant galaxies are moving away from us. This, it is said, is due to expansion of space. Additionally, dark energy is said to cause this expansion of space to accelerate. Everything that the Big Bang claims stands on the shoulders of this interpreted motion of distant galaxies away from us. It means that if we reverse time, then we can envisage the galaxies coming back together closer and closer until they are all part of one single particle or source or nothing from which the universe had a Big Bang into existence. Moreover, it suggests that the age of the universe is finite, typically cited at around 13.8 billion years. It leads us to interpret several other observations in light of this model, such as the cosmic microwave background, and attribute additional Big Bang characteristics to observations outside of redshift. What it does not mention, however, is that this is based on an assumption, specifically the assumption that motion is the cause of the observations behind these concepts to begin with. When we observe distant galaxies, we do not see motion away. Rather, we analyze the light spectrum of these galaxies to determine what their composition is. When we do this, we see absorption lines that tell us what the galaxy is made of. These absorption lines are at very specific frequencies locally on Earth. However, distant galaxies have their absorption line patterns shifted to lower energy in what is known as a redshift, as shown in Figure 2 previously. This shift of absorption line patterns is what we actually see. Redshift can occur by motion away from an observer in what is known as Doppler shift. However, it can also be caused by gravity in what is known as gravitational redshift. Thus, the big assumption is that motion is the cause and gravity is not. This led to the conclusion that all distant galaxies are moving away from us. Therefore, they were once all together. Therefore, there was a Big Bang. It is important to note the history or the evolution of the theory. In its original form, Doppler shift in and of itself was sufficient to explain the observations. The concept that space was expanding was not introduced until there was a distinct need for it, high redshift values. These redshift values were at times seen so high that they would imply faster than light travel of the galaxy away from Earth. It was also seen that there was a relationship between how high the redshift of a galaxy was and how far away it was, which gave a means to insert expansion into the model. To correct for the apparent breaking of the laws of physics, this correlation of redshift per distance, recognized by Georges Lemaitre and Edwin Hubble, which came to be known as Hubble's law, as shown in Figure 9, was extracted from redshift observations. This linear statistical distribution of redshift per distance was then labeled cosmological redshift, differentiating it from conventional redshifts and attributed to a completely new phenomenon, expansion of space. So we just look here, redshift per distance. Noticeably, as we look further in space, we see a relationship that the further away a galaxy is, the more redshift it is in a seemingly linear relationship, which is known as Hubble's law. It is important to take careful note that the observation, which is the degree of redshifting in the absorption line patterns from distant galaxies, is so commonly translated as velocity or recessional velocity that it is typical and standard procedure within academia to represent redshift in the above manner as velocity in kilometers per second. This means that the observation, upon being grafted, carries with it the assumption that motion is the specific cause of the redshift values observed. Interpretation has worked its way into science in this way in many places, and this is an exemplary case of the common practice of translating data rather than reporting the data. As redshift can also be caused by gravity, which will be elaborated on in a moment, it is an assumption to claim the redshift to be based on recessional velocity. Let us look at another example to understand the significance of this assumption. Imagine that you and I are in a room together, both having access to the same cookies. Someone is consistently monitoring the number of cookies eaten, and they notice that over time, more and more cookies are consumed. They see you and think, aha, you are the cookie consumer. Meanwhile, you had not even noticed the cookies, and I was the one eating the cookies. Then many people begin to do studies of the amount of cookies you consume across time, coming up with graphs that depict time on the x-axis and your cookie consumption on the y-axis. In reality, the studies have mistakenly labeled general cookie consumption as specifically your cookie consumption simply because they know that you can consume cookies. The same is the case with redshift, where what is seen is general redshift, but it has been labeled as specifically redshift due to motion. In this way, the data has been taken further than it actually indicates, and assumptions have found their way into the actual graphical and textual representation of the data. As a result of the assumption that motion causes redshift, and the subsequent interpretation of cosmological redshift as a result of expansion of space, the Big Bang model does not pass the sharpness factor test. This is because it is more dull, requiring the additional element of expansion of space. This means that at the point of the sharpened proverbial pencil of the Big Bang, there are more components than previous models. Therefore, it is illogical from this alone. However, it did not stop there. More recently, due to increases in the capacity of our telescopes to see further into space, it came to be recognized that the rate of redshift per distance was not linear as was implied by Hubble's law. Instead, the rate of redshift per distance detectably accelerates at larger distances. In terms of the Big Bang, this implied that the rate of expansion of space was accelerating. To explain this, an inexplicable force was introduced, dark energy. This is why labeling this correlation as Hubble's law is a drastic overstep in what it truly represents. It is a correlation that exists over a certain range that can be approximated as linear within that range, but over larger distances, the linear correlation is broken as it becomes apparent to be an exponentially increasing correlation. In short, it is not actually linear. Mistakenly, it was proposed that the linear correlation was somehow universal, and that led to the interpretation that any deviations therefrom had separate causes. This is not how universal laws function. A law would describe both the rate of redshift per distance and the accelerating rate of redshift per distance and apply universally. This is what it means to be a law. Hubble's law is a distance-dependent correlation. The labeling of this correlation as a law has played a non-trivial role in translating its cause as expansion of space. Without the law, only with a correlation, then the universality of expansion of space would be drawn into question because the observations to which it was ascribed would be recognizably not universal. Regardless of what it is labeled as, the correlation is not universal due to the accelerating rate of redshift per distance seen at sufficient distances from Earth. Throwing dark energy on top does not remedy this. Dark energy, it was said, was an unknown force that led to the accelerating rate of expansion of space. This made the Big Bang's sharpness factor even duller, having yet another fundamental characteristic of the universe required. The objective of science is to narrow and simplify explanation, not to expand and complicate. Therefore, interpreting observed redshift of distant galaxies to be the result of motion is an extremely big assumption. If gravitational redshift could be shown as capable of causing the redshifting, it would thereby disprove the existence of both expansion of space and dark energy, as they would be seen to be the results of misinterpretations due to an invalid assumption. This would additionally improve the sharpness factor by not requiring the existence of these two elements at the sharpened tip, since gravity could be used to explain the redshift without adding any other fundamental interactions. The observation of redshift per distance for all distant galaxies is importantly in all directions. This made it much easier to interpret the redshift as the result of motion rather than gravity. However, the possibility that gravity is the actual cause is strongly supported due to the motion-based interpretation's need for the introduction of more complications to the model, as in the Big Bang. The question then becomes, how? When light moves away from a source of gravity, the force of the gravity pulls on the light and stretches it into a redshift. When light moves towards a source of gravity, the force of gravity pulls on the light and compresses it into a blue shift. Gravitational redshift is unrelated to motion of the galaxy emitting the light, but rather is due to influences of gravity that the light experiences while it is traveling from its source to its destination, as shown here in figure 10. So just the source of gravity and then light generally moving away from it. Nothing to do with the actual galaxy that's emitting the light. It's just once the light is emitted, if it's moving away from a source of gravity, then it is redshifted by that source of gravity. There was no immediate explanation for how gravitational redshift could produce the observations, and so it was assumed that it did not, and thereby, through deduction, the conclusion was that motion must. After all, it does appear that way at first glance. Again, this assumption led to a more complex model. However, gravitational redshift can produce the observations of redshift per distance of galaxies in all directions, and due to not needing additional explanations, it does produce the observations. How it does this is literally not straightforward, and thus, without careful consideration, the mechanism behind it was not recognized. The universe is the manifestation of infinity, having ever smaller and ever larger objects. This can be arrived at from simple pattern inference. We recognizably see that the moon orbits the Earth, which orbits the sun, which orbits the supermassive black hole at the center of our Milky Way. This pattern implies that logically the Milky Way galaxy should orbit another larger mass, and that should orbit a larger mass, and so on, ad infinitum. This pattern would also go in the opposite direction, always smaller, ad infinitum. Indeed, this is how the universe functions. The recognition of redshift per distance in all directions of Hubble's law is significant because it means that if gravitational redshift is causing the observations, then it is caused by one single object, and a large one at that. If many objects were behind the redshifts, then each would have different weights and would arrive at different degrees of redshift per distance due to their varying degrees of gravitational influence, and so no correlation would exist. Only in the instance where the gravity of a single object causes the redshift of the light from all galaxies could a detectable correlation arise. Therefore, the question then arises, how does a single object produce all distant redshifted galaxies in all directions by gravitational redshift? As this larger mass would be in one position relative to Earth, on the surface, it would appear that it is only capable of producing redshift in the light coming from those galaxies in its direction. The light traveling to Earth would move away from this object and thereby be redshifted. However, the galaxies on the opposite side of Earth relative to this object would emit light that travels towards this object in order to reach Earth and would be blue shifted, creating a dichotomy of essentially half redshifted and half blue shifted galaxies. Notably, within a relatively short distance in what is known as the local group, we do see this dichotomy. The Shapley supercluster has the largest galaxy concentration in the nearby universe that recognizably forms a gravitationally interacting unit. In the direction of the Centaurus constellation, this conglomeration of galaxies exists along with what is known as the Great Attractor and the Centaurus cluster. In the local group, light coming from galaxies in the direction of these systems is mostly redshifted, and light coming from galaxies in the opposite direction of these systems is mostly blue shifted. This dichotomy is proposed in the Big Bang model to be due to a flow of galaxies in the local group. However, this interpretation stems from the assumption that the shifts in the light spectrum that we see from these galaxies is caused by motion. In the alternative, if we suppose that cosmological redshift stems from gravitational redshift caused by a single system, then the hypothesis becomes that one of these systems is overwhelmingly the cause. The Shapley supercluster is the largest system in the nearby universe and therefore is herein proposed as the most likely source of gravitational redshift of all galaxies that we observe. This is evidenced through the dichotomy with respect to its position. How then can one system which is in one position relative to Earth, which produces a dichotomy of half redshifted and half blue shifted galaxies in the local group, produce all distant redshifted galaxies in all directions? The missing link here is what is known as gravitational lensing. When light is influenced by the gravity of an object, its direction of travel can be bent so that it curves due to the gravity of the object. This occurs, for example, in what is known as an Einstein cross. So in this image, we have a galaxy at the center, and then behind it, beyond it, is a quasar, and that quasar's light is being bent into basically 4 optical illusions of the one single quasar. And this is an example of how gravity can bend light. This interaction was first proposed by Isaac Newton. Do not bodies act upon light at a distance and by their action bend its rays? And is not this action strongest at the least distance? The recognized source of gravitational lensing is typically a galaxy or group of galaxies because of their mass. However, this does not consider the universe to be infinite in nature. Light is not lensed substantially by lower mass objects at larger distances of separation, but as we approach the mass of galaxies, light is more and more obviously lensed. However, What would happen to light if an object that was so high in mass that entire galaxies orbit around it were to lens said light? If an object were sufficiently massive, it would be capable of lensing all light from galaxies in a volume that we perceive as large in the universe. And if it were sufficiently massive, it would be capable of lensing all light from galaxies back to it. In such a case, the path of travel of light around the object, if the light were to be able to travel through the object, would follow the same figure-8 orbital structure as the particles that make up the electromagnetic field of an object. In fact, the light would be part of the object's electromagnetic field. And after a portion of traveling a single time through the orbital or many repetitive full orbitals, light would be capable of reaching Earth from any angle. This would mean that over short distances, such as those in the local group, the light would be incapable of substantial gravitational lensing because it is not exposed to the gravitational effects for sufficient periods of time so as to become greatly lensed, forming only a nearly straight portion of a figure-8 segment. Over larger and larger distances that the light travels, it would become so substantially lensed that it does not travel in a generally straight line to reach Earth, but rather travels in a figure-8 orbital about this object. As a result of this figure-8 structure by which the light travels, it would be capable of arriving at Earth from any angle and at increasing distances. What is most interesting about this seemingly hypothesized trajectory of light arriving at Earth is that the more times the light travels through the figure-8 orbital structure, the more it would be gravitationally redshifted. This can be envisioned most easily by separating the motion of a single loop of a figure-8 into radial motion from the center and orbital motion about the center. From the standpoint of radial motion, there are equal but opposite motions outward and inward in the travel of light in this manner. As a result, the redshift from radial motion away from the central object would be equal and opposite to the blue shift from radial motion toward the central object when a full loop is traveled. However, the orbital portion would always produce redshift. This can be thought of alike to a planet orbital. At any point, if a planet were to suddenly stop being influenced by the gravity of the object it is orbiting, it would start traveling away from the object it is orbiting. This is because orbital motion is always away. Due to this phenomenon, light traveling in a figure-8 orbital about an object in this manner would be additively redshifted with each pass through a loop of the figure-8. In other words, this would produce increasing redshift per distance. Due to a singular object being the cause, it would lead to a detectable correlation, and due to light being capable of arriving at Earth from any angle within a figure-8 trajectory, it would produce all distant redshifted galaxies in all directions. If this were to be happening, it would mean that, generally speaking, at larger distances, we would see more and more galaxies. This is because when light travels short distances, it is incapable of taking many different angles to reach Earth because it must travel in essentially a straight line. However, over large distances where the light is bent, a single galaxy can emit light in many angles where it will ultimately arrive at Earth. This would give the appearance of there being more galaxies when we look out further in space. Moreover, it would give an appearance of a generally spherical area around Earth having lower density of galaxies. The KBC void is a comparatively empty region of space with the Milky Way generally at the center. This is an area of underdensity that spans approximately 2 billion light years in radius. This is the largest void known to science and is roughly spherical in shape. It is important to note the oddity of our presence near the center of the largest void in the observed universe. This strongly suggests the void to be observer dependent rather than an actual void. With the shapely supercluster approximated at 650 million light years from Earth, the void diameter is in line with an interpretation where the figure 8 return of light from galaxies is necessary in order to begin to see more and more optical illusions. When light arrives at Earth from a distant galaxy, we assume it has traveled in a generally straight line. Therefore, when we create a map of galaxies, we physically position galaxies based off of the angle at which the light arrives and the detected distance the light has traveled. This does not in any way account for large-scale bending of light due to sufficiently large mass objects. As a result, we map a volume away from Earth that appears to be under density, low in galaxies, because we are not properly positioning the coordinate location of the galaxy when it emitted the light. This would be akin to interpreting each of the quasars of the Einstein cross as its own distinct object and creating a map with each. With an Einstein cross, we can see the apparentness of the lensing due to the proximity of the observations, and so we recognize only the single source exists and not four. But in the case of lensing to the degree of a figure 8, where the apparent position of the galaxy emitting the light can be anywhere, we interpret these galaxies as distinct and different. In three-dimensional coordinate space, the observed galaxy does not exist where it appears. Rather, it likely exists as a much closer galaxy, one which we see as being in the local group or in the general area of the shapely supercluster. Those beyond show themselves to be optical illusions by following the correlation of redshift per distance produced by gravitational redshift on figure 8 light travel. This means that we can see the same galaxy at several different times in the past because of the large range of varying distances light from a single galaxy can travel to reach Earth. Not just as slightly varied, but spanning billions of years of its history. In fact, it means that we can even see our very own Milky Way galaxy from the outside across its history. By using the same explanation for how gravity causes electromagnetic fields in a model to explain how gravity causes all distant redshifted galaxies, the sharpness of the infinite model is greatly improved over standard models due to reducing the fundamental cause of both electromagnetic fields and all distant redshifted galaxies in all directions to being gravity in one fell swoop. Therefore, space is not expanding, and thus nothing is causing the rate of expansion of space to accelerate because space is not expanding. This means that dark energy is in a misinterpretation as well, and the question then arises, how does gravitational redshift produce accelerating redshift per distance at large distances? At large distances, all light from distant galaxies that follows the detection or the detected correlation of redshift per distance is doing so because the light is traveling in a repetitive figure 8 orbital. This means that with each pass through, the light is more redshifted than it was when previously in the same position in the orbital pattern. This suggests that as light redshifts, it leads to greater redshift per distance within the figure 8 orbital structure. We will revisit why this is later after a more thorough discussion of the environment. Infinity. And so that's the end of chapter 2. Now we're going to get into more philosophical stuff about infinity in chapter 3. So thanks for listening, and talk soon.